Let n be an integer greater than or equal to 3. Rowan and Colin play a game on an n by n grid of squares, where each square is colored either red or blue. Rowan is allowed to permute the rows of the grid, meaning that he can rearrange the order of the rows, but not the elements in each row. And similarly, Colin is allowed to permute the columns. A grid coloring is called orderly if, no matter how Rowan permutes the rows of the coloring, Colin can then permute the columns to restore the original grid coloring, and vice versa. No matter how Colin permutes the columns of the coloring, Rowan can then permute the rows to restore the original grid coloring. In terms of n, how many orderly colorings are there? So the problem statement looks kind of scary, so let's try for n equals 3. So we're looking at n is equal to 3. Then we have a 3 by 3 grid of squares, which I'm drawing here. And each square is colored either red or blue. So let's suppose we have like these squares are colored red. And then the square is colored blue. Then let's try looking at the first condition here. So let's try permuting these two rows to get that the blue goes down here. So now this here is blue and this is red. Then the blue is stuck down here, and no matter how Colin can permute the rows, the blue will still be on this row. And we cannot get to our original grid coloring because the blue is supposed to be on the top row, unless there's a blue on this row as well. So let's go ahead and make one of the ones on this row blue here. Let's say this one. So now that we have our blue one here, now let's try considering this row, which still has only red. Then we have, if we swap these two rows, we similarly see that there must be a blue inside this one. So there, let's suppose that the blue is over here. Now we look at the second condition. No matter how Colin permutes the columns, Rowan can then permute the rows. Then this one here has no blue, so we can swap around these columns, which implies that this also has a blue. So suppose that the blue is over here, suppose. Then now we apply this thing again, and we can swap these two rows. And in general, we conjecture that any two rows and any two columns must have the same number of blue cells. So here is our conjecture. So conjecture, every row has the same number of blue cells. So how do we prove this conjecture? Well, we can use some arguments similar to what we're doing here. So in an n by n grid, we can generalize for n is greater than or equal to 3. If we have two rows that have a different number of blue cells, suppose that we have like our rows here, and then there's this one with A blue cells, and then this one here with B. And suppose that B is not equal to A. Then that means that Rowan can swap these two rows. Then this will become B, and this will become A. And no matter how Colin switches around the columns, this row will still have B blue elements, and this one will still have A. So therefore, if B is not equal to A, then the first condition cannot hold, which implies that B equals A. Repeating this for every single row, we end up getting that this conjecture holds. We similarly see that this conjecture holds for every column as well. So now we've discovered the following. Every row has the same number of blue cells, say R. Similarly, every column has the same number of blue cells, say C. Now we will count the total number of blue cells in the grid, because we want to somehow relate R and C. Then this here, if we sum everything by rows, there are blue cells per row and n total rows, so that gives Rn blue cells. And this similarly gives Cn blue cells. Therefore, these two quantities are equal, and so R equals C. So since R equals C, we now have that this holds. Therefore, every row and column has the same number of blue cells, say k, and we know that 0 is less than or equal to k is less than or equal to n. That is obvious. So now let's go ahead and try casework on k, because that seems like the only obvious way to go. So if k equals 0, then that means that there are no blue cells in the entire grid, and the entire grid is just red. And this clearly works since permuting the rows doesn't do anything at all. So that works, and that gives one case. If k equals 1, then every single row and column has exactly one blue cell. So we are looking at something like this if we have our huge grid. Then we have some blue cells scattered across everywhere, such that no two blue cells lie in the same row or column. And this works since every single permutation of the rows is just a permutation of the columns. For example, if we swap around these two rows, this one and this one, then that will yield this one and this one here. But that also results in swapping around these two columns here. Therefore, we know that every single permutation of the rows corresponds to a permutation of the columns, and similarly, every permutation of the columns corresponds to a permutation of the rows. So all of these guys of this form work here. So, and there are n ways to choose the blue cell in here. Then, since this row is now eliminated, there are n minus 1 slots for here, then that's eliminated. Then n minus 2 slots for here, then that's eliminated, and we continue going on. So this is n times n minus 1 times n minus 2, all the way until we're forced to have one slot for the last blue. And that gives n factorial. Now let's move on to k equals 2. This case is kind of complicated because now we want to try finding one where such a permutation exists. Then if we have k is equal to 2 here, then let's go ahead and try looking at n equals 4, 2, because that will be the first case where it has a noticeable effect. Then we have a 4 by 4 grid here. And then there are some blues and some reds in every column. So we could have something like this. And like a checkerboard, for instance. Then all the rest are red. Then now let's consider the first condition. If Rowan swaps two rows, then he could swap around this one and this one. Then that will yield something like this. Now if we want to swap around the columns in order to make it into this again, then we have to swap around this red pattern here to get another red pattern here. However, if we have a red pattern in a column, we cannot change around the red pattern in the column. And we have the reds that are two next to each other, then two reds that are one apart from each other. So there's no way that we can rearrange it into that. Using the patterns argument, we have shown that this configuration here is not orderly. And this motivates us to try generalizing this argument to all n and all k. So let's do so. We will consider the patterns that the blue elements make here. So let's first number the rows, the columns from 1 to n, and similarly, let's number the rows. Then we can describe each row with the blue configuration as an ordered k-tuple. That is, we have x1, x2, all the way to xk, where x1 is less than x2 is all the way less than xk. And these are the cells in which we have the blue cells. So inside the first row, we'd have x1 equals 1 and x2 equals 3 and k equals 2, obviously. Then we only use n of these total. However, that there are a total of n choose k of these, which means that we have that if n choose k is greater than n, so n choose k is greater than n, then one of these guys is not used. So let's try using that to our advantage. So that means that Rowan can first permute the rows of this thing and therefore rearrange it into the one that doesn't appear. So one doesn't appear, and Rowan rearranges the rows such that the first row has the one that doesn't appear. Then no matter what Colin does to rearrange the columns, he cannot get rid of that pattern inside the first column. And therefore, that means that if n choose k is greater than n, then we do not have an orderly configuration. This implies that k is greater than or equal to 2 or k is less than or equal to n minus 2 is impossible. Now we have shown that 2 is less than or equal to k is less than or equal to n minus 2 is impossible, since in that case n choose k is greater than k. Now we have only two cases left to consider. There's k equals n minus 1, which is practically similar to k equals 1 because we just repeat this argument with the blues, but instead with the reds. So that gives n factorial. And we have k equals n, which just gives a blue grid. And that gives 1. Therefore, if we sum up all of these cases, we have our answer is 1 plus 1 plus 1 n factorial plus n factorial, which is 2 times n factorial plus 2. And that is a number of orderly configurations in terms of n. So thank you so much for watching this video. Please subscribe if you'd like to see